Now we come to the third lecture of uh, the course NE402 Intermediate Nuclear Engineering, uh, focusing on diffusion and transport of radiation and Monte Carlo simulation. This is week 1, lecture 3, Introduction to Nuclear Engineering, and this lecture is on nuclear reactors and criticality. Again, my name here and my personal email, official email, and my personal website, www.nucleareng.com, my cell number. And as I said in the previous lectures, I'll be more than happy to take your questions, to correct any mistakes that I may have made over here. And I hope that these lectures serve their purpose of essentially teaching the concepts from an engineering perspective. So let's begin with nuclear reactors. Now, nuclear reactors, so first let's talk about nuclear power reactors. A nuclear power reactor uses the thermal energy from a nuclear fissile fuel and converts it into electrical power. And this is the electricity that we get in our homes. So the process is, as in all engineering systems where you produce energy, that you convert from one form to the other. So there's the first law of thermodynamics, which says that energy can neither be created nor destroyed. It can change the form. So here what we do is we go from thermal to mechanical to electrical. Just like in the engine of a car, or when you burn coal, when you burn oil, when you burn gas. So nuclear power is the same, that you have nuclear fission. Now, the fuel is something which undergoes nuclear fission reactions. And as I told you in lecture 1 and lecture 2, the amount of energy coming out of nuclear fission is very small, but when you multiply it by the number of atoms, the number of nuclei, then it becomes a big number. And we can use that electricity to power our cities and so on. So one way of achieving this conversion is to transfer thermal energy to a fluid, such as water, convert it into superheated steam, which would go into a turbine to rotate a shaft. And you know that if you've got a stator and a rotor, then you can generate electrical charge, and that's called an electric generator. Now, commercial nuclear reactor development began in the late 1960s, and reactors of those days are called the first generation reactors. They evolved into bigger, typically 1,000 megawatt electric designs in the second generation. And as of this month, June 2020, when I'm making these lectures in the days of the coronavirus that we're going through, so this month, according to the International Atomic Energy Agency, there are 441 operational nuclear reactors with over 390 gigawatt electric installed capacity. The contribution to the world's electricity by nuclear is about 10%. The most is coal, which is 38%, followed by natural gas, 23%, followed by hydroelectric, 16%, followed by nuclear. So nuclear is the fourth in the world. And then you've got oil, which is 3%, wind 4%, solar 2%, biofuels and waste 2%, geothermal and tidal 1%. So over 100 of these operational reactors are less than 10 years old, and 85 are over 40 years old. So that's also a serious concern, because just like human beings, engineering equipment also has a life, and then you have to do what is called re-engineering. So in the first and second generations, the reactor designs were improved, and we came to Gen 3 and Gen 3 Plus designs, such as IRIS and AP1000, and better designs have evolved. At present, 54 reactors are under construction, with 11 in China and 7 in India. Now, looking further, efforts are underway to develop prototypes for the Gen 4 designs. So just like mobile telephones have generations, and you're coming to G5, so in nuclear we're talking of generation 4, G4. Now, G4 is around the corner, maybe 5 to 10 years, and this will meet the challenge from renewables, which everybody says are cleaner and so on. So nuclear is now coming with new designs to compete, to make a market for itself. And these designs are going to be competitive and acceptable, and they will most probably lead to a nuclear renaissance after the negative publicity that nuclear power has received. Now, let's see those 440 nuclear reactors. How are they classified? Well, most of them are converters. So they use a fuel and they have fission and they convert it into energy. Thermal reactors, so there are two kinds of, let's say we can categorize thermal reactors and fast reactors. As I said previously, thermal means energies which are thermal energies, 0.025 electron volt. So these reactors are the majority in the world, and there are light water reactors. A further division is that there are pressurized water reactors, PWRs, and boiling water reactors. Then you have gas-cooled reactors, the advanced gas-cooled reactors, and the old gas-cooled reactors. Then you've got a pressurized heavy water reactor, the CANDU Canadian design. And these reactors are classified based on the fuel that they use, the moderator, the coolant, whether it's enriched fuel, whether it's natural fuel. For example, the Canadian pressurized heavy water reactor uses natural fuel, whereas PWRs typically use 3 to 4% fuels. Now, about 80% of operational reactors fall under the light water reactor category. 60% of the reactors in the world are pressurized water reactors, and about 20% are boiling water reactors, while the remaining include pressurized heavy water reactors, gas-cooled reactors, and one or two fast reactors. These include similar designs, such as the Russian PWR and RBMK boiling water reactors. So those are the Russian equivalent of the Westinghouse and Babcock and Wilcox designs. Now, we have become environment conscious, and so we say that you should have near zero greenhouse gas emissions. So, so that's why modern nuclear reactors are being designed and are at various stages of development. So the evolutionary designs are the advanced boiling water reactor, the simple economic boiling water reactor by GE, and the Advanced Pressurized Water Reactor, AP, by ABB and Westinghouse. Now, so these have features which I won't go through in great detail, but the thermodynamic cycles that you can have in reactors are the well-known Rankine steam cycle, and you can have the gas Brayton cycle. You can also have combined cycles to increase the efficiency. So 30 to 42% you could try to achieve in terms of thermal to electrical efficiency. So there are also the categorization of fast neutrons, which means that the flux is at a higher energy. And apart from power reactors, as I said, there are over 440 power reactors. So there are over 800 small research reactors, including critical and subcritical assemblies. They're spread over 67 countries, and they're used for basic scientific research, for development, for the production of isotopes, as nuclear engineering has a very diverse area of applications in medicine, agriculture, forensics, and so on. So let's look at nuclear reactor components. Now this picture I've taken from Encyclopedia Britannica. And so this shows you a man standing next to the core of a pressurized water reactor. Now this is to give you a little picture. So this is a cylinder, it's a vessel, and we call this the core, the reactor core. Now inside the reactor core, you'll see lots and lots of assemblies. So these are called fuel assemblies. So there's an upper plate and there's a lower plate, and in between these there's a crane on top. So this is a vertical reactor, so the crane puts the fuel down. There's a moderator that moderates fast neutrons, makes them thermal, because as I told you, the fission cross section is high. Remember in lecture 2 we looked at the fission cross section of U235 at thermal energies was about 580 barns. So that was very good compared to what it was for the fast spectrum. So most of the reactors in the world now, the power reactors are large reactors. So a typical 1000 megawatt electric, meaning about 3000 megawatt thermal pressurized water reactor, would have in a pressure vessel of inner diameter 4 meters, it would have 157 fuel assemblies with 17 times 17 rods per assembly. The total number of rods would be 45,000, and the active fuel length it would have would be about 4 meters. So each fuel assembly would have a rating of about 20 megawatt thermal. So multiply 20 by about 150, that's about 3000 megawatt thermal, and you would produce 1000 megawatt electric. So that's good for a city of about 1 to 2 million people. Now, the total fuel in such a reactor could be about 100 tons, and the amount of fuel varies depending on the power, the type of reactor, the enrichment of the fuel, etc., etc. Now, this very large amount of heat, which is produced by nuclear fission reactions, can be removed. In a PWR, it is removed by the flow of large amounts of coolant, such as water. So you take this huge amount of water, which is 67,000 cubic meter per hour, and you circulate it. So the thermal energy of nuclear fission goes into water, and you know when you heat water that if the heat is sufficient, then you can convert water into steam. Give more heat, you can convert it into superheated steam. Superheated steam is strong, it's energetic, so you can make it do mechanical work. So a reactor core would have coolant pumps, it would have a coolant. The materials in in nuclear engineering cover from the front end of the fuel cycle. Now, I've not said anything about the front end of this fuel cycle. Now, this means from where it is taken out from the ground, the uranium ore, it is converted into fuel. So this is called the front end of the fuel cycle. So uranium ore is converted and enriched for reactor fuel fabrication. Now, just as you have the front end of the fuel cycle, you have the back end of the fuel cycle, which means after the fuel has been used, it has been, so as we say, burnt to some extent. It's hot, it's got lots of radioactive material, so you want to remove it. You put it in a swimming pool, you put it in a storage facility, let it cool down, and so that's the back end of the fuel cycle. And then you can recover some of the burnt fuel. Now U238 converts into plutonium. Plutonium is a very useful thing. Some thorium, if you're using thorium in some reactor, thorium-232 can convert into U233, which is almost as good as U235. So a nuclear reactor would have a core, it would have a coolant facility, then it would have a turbine, and then it would have recirculation of the cooled steam, again becoming water, condensing to water, and then you would have 1 or 2 cycles. You would have direct cycle or indirect cycle, and you would basically transfer the heat out of the core into the steam turbine, into the secondary side. So there's a primary side and a secondary side. Now, in the front end of the fuel cycle, the yellow cake, as it's called, the U308, which is in so many countries of the world, Australia, Canada, Niger, so it's in China, it's in so many countries of the world, so it's taken out of there. And the uranium in mixed oxide form is chemically processed into uranium tetrafluoride and then into gaseous uranium hexafluoride. Now, UF6 is a gas, and uh, you can enrich it. In other words, you can increase the U235 content because in natural uranium, it's only 0.7%, which is U235, and 99.3% is U238. So gas in, gas out goes into a centrifuge plant, for example, and a typical enrichment process with an ideal cascade input of 8 kilograms of natural uranium with 5 separative work units would give you 1 kilogram of uranium, 3.7% uh, enriched, and it would give you 7 kilograms at 0.25% enrichment. Now, the fuel required in nuclear reactors, in the old days, it was metallic fuel, then oxides, then now you have nitrides. In the next generation, nitride fuels are being considered, and there's also promise of molten salts of uranium. Uh, and so when we talk of enriched fuel, then we say that anything up to 20% is what we call reactor grade uranium and reactor grade plutonium. Now, above 20% is not done for power reactors because you go into higher enrichment, and 90% is for weapons. And I'll just show you that new reactors, small reactors, are being considered micronuclear reactors with up to 60-70% enriched fuel. So these are the chemical processes by which uranium is converted to a form where it can be used. Now, apart from power production, there are many other uses for nuclear power apart from big power plants. So they've been used in naval propulsion, and they're now used for space exploration. And so one of the earliest uses of nuclear power has been for naval propulsion. In 1955, the first nuclear-powered submarine, the USS Nautilus, was put to sea, and since then there are over 120 ships which are powered by more than 200 small nuclear reactors. These nuclear reactors are used for propulsion, they're used for icebreakers, they're used for aircraft carriers. Now, when you go to space, because that's another fascinating frontier, that going to exploring the moon and going to Mars and seeing whether to learn about Mars. Was it ever a planet like Earth? Can humans go and live on Mars? So for for such applications, very small prototypes are being developed. Now, one such by Los Alamos for NASA is a 5 kilowatt thermal. So that's about 1 kilowatt electric. So 20% efficiency. It's called Krusty Kilopower Reactor using Stirling technology. It's fueled with a solid core, highly enriched uranium, which has been demonstrated. Now, they've also looked at more than 5 kilowatt thermal. They look at 50 kilowatt thermal with 20% thermal to electrical efficiency, with 93% highly enriched uranium, and also with low enriched uranium, less than 20%. The highly enriched uranium reactor has fuel plus a reflector such as beryllium oxide, and they report weights as low as 161 kilograms, 268 kilograms, respectively, for the 5 and 50 kilowatt thermal, out of which the U235 uh, and fuel are 28 kilograms and 38 kilograms for the smaller one, and 38 and 44. So that's 28 kg U235, 33 kg total uranium, and 38 kg U235 and 44 kg for the 50 kilowatt design. Now this compares, if you want to compare with a larger uh, reactor, but that's a design of 2400 kilowatt thermal, and out of which you can get 120 kilowatt electric. Now, these designs are being considered. There's a 70% enriched uranium nitride fuel reactor, Its core weighs 310 kg. Now, why is weight so important? Because you've got to carry it on a rocket which will leave the planet Earth, it will go into space. So you'll have to transport it all the way from here to Mars, which is about 55 million kilometers. And if you don't have, of course, you won't have water over there probably, so you will not be able to produce steam. So they're looking at non-moving part systems. And one possibility is a thermoelectric generator, TEG, which converts energy directly from heat to electricity. And I told you previously that the PWRs go from thermo to mechanical to electric. Now, these reactors do not have the mechanical part in between because they're trying not to have moving parts. Moving part means maintenance and chances of failure, etc., etc. So small designs are being considered for space with thermoelectric generators, solid state designs. Now, there are advantages of using uranium nitride fuel, and you can look at a paper by Wang et al. In Annals of Nuclear Energy. One of the latest papers gives you a design for 500 kilowatt thermal, out of which you can get 25 kilowatt electric with 65% enriched uranium nitride fuel. Now here they use novel concepts for removing the heat. They're using heat pipes. Now heat pipes are used. The concept of heat pipe is that it's like the candle, like uh, like the little tube that you see, the little cloth inside a candle which burns. So that's a kind of wick. The wax melts, it vaporizes, goes into the across the wick into the central part, rises up, and that's how the candle burns. So the same thing they're trying for heat pipes in nuclear reactors, that you have a coolant, something which can operate at a high temperature, like liquid metal such as sodium, and you have some liquid metal which will vaporize, go into the central region through a wick, and rise up and transfer the heat from the core to possibly a thermoelectric generator or a Stirling engine. Now, other more fascinating areas for youngsters, especially looking for interested in nuclear engineering and looking ahead the next generation, are small modular reactors and advanced micronuclear reactors. Now, small modular reactors mean reactors with power generation less than about 300 megawatt electric. And there are already PWRs which are operating at 300 megawatt electric. So these provide flexible and affordable power, and you can place them where they're needed. So that's a good thing, that they don't need to be far away from where they're needed. And they could be built in modular forms. Now, there are presently about 50 SMR designs being studied globally, and they're at the various stages of development. Now, I'm going to talk to you about two particular designs which are fascinating. One is the 4S Toshiba design. The 4 S's stand for super, safe, small, and simple. Now, this Toshiba design, you can see papers by Ueda, Suboi. This is a sodium-cooled Gen 4 reactor, fast reactor, which means that it does not slow down. The neutron spectrum is at a MeV region. So this is aimed for sealed operation for a period of approximately 30 years. And if you look at the design, it's fascinating. It's small, and it's relatively free from the risk of fissile material proliferation. They have designed a 30 megawatt thermal reactor and a 135 megawatt thermal reactor with electrical outputs of 30 megawatt and 50 megawatt respectively. Now, these advanced systems have many advanced features such as passive safety. Passive safety means that if electrical things fail, if motors fail, then things should fall down by Earth's gravity, and it should shut down safely. So there are many safety systems in this, and it's a low enriched uranium reactor, which means that it's less than 20%. Now, there have been more fascinating and smaller studies for batteries, for nuclear batteries. So the world could look at in future for small nuclear power, and you could have small microgrids because there are millions of people who live off grid who've never uh, had the benefit of electricity. There are specialized applications such as desalination, and so there are many advantages of such small reactors. Now let me just take you through the basic uh, design parameters of a reactor. So first of all, I think I should show you a picture from the top. So here's a picture of this reactor. Now, if you look at the X and Y axis, so this is in centimeters, so 0 to 60 centimeters. So you're looking at a vessel from the top, a cylindrical vessel, which has a diameter of about 1.2 meters. So that's just uh, over 3 feet, so less than 4 feet. So you're looking at this and see there's a control rod in the center, the light blue color, and the yellow region is the matrix that it's in. It's the moderator, which is sodium. So sodium is well, you don't need to moderate it that much, but sodium is also a coolant over here, and you've got 6 hexagons in here, and you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hexagons at the outer periphery. Now, these have fuel rods, and the green is the reflector beryllium, so that when neutrons are escaping, it reflects them back. Now, this is the control of the reactor. So when the reactor starts, so we gradually take the control rod out, we pull it out, because reactor fuel burns, and when it burns, then excess reactivity is reduced. So we pull the control rod out, and it's designed in such a way that the first 15 years, the control rod is gradually lifted outwards. Now, this is what I was talking about, the passive safety feature, that if everything fails, it's going to fall straight back into the core, and the core is going to shut down, so there's no danger. Now, the next 15 years, the reflector is going to come up and reflect the neutrons back. So if you look at the parameters over here, you can see how much fuel is involved. So in the inner zone, the fuel is uranium-10 zirconium, and the diameter of fuel rods is about 1 centimeter. The die is 1 centimeter. The height of a fuel rod is about 2.5 meters. 169 assemblies here, 169 outside, so 6 and 12. So the total amount of uranium that you've got sitting in the core is about half a ton U235 inside and 1.17 tons outside. So you've got 1.7 tons of U235, and the total is about 3.5 plus 8, so it's about 11.5 tons of uranium, less than 20% enriched. And the coolant, as I mentioned, is molten sodium, and the reflector is beryllium. These are the number densities which I mentioned in the previous lecture, that you have to calculate for your fuel the number densities. And this is what I did. I calculated the number densities for this to carry out the simulation. And this is a published paper in the Annals of Nuclear Energy. So you can see a little bit on the design of this nuclear reactor. So it's a paper by myself. So you can look at Annals of Nuclear Energy 4S design by Koreshi and Hussain. Okay, now smaller than this, is nuclear power possible? Well, yes. And if you look at another revolutionary and evolutionary design which combines space with power reactor features, then it's the design of Westinghouse. And they've named it eVinci. So it's a trademark design, and this is roughly what it looks like. So this is another simulation that I carried for a design by Wang. And this is latest research, 2019, 2020. And if you look from the top, the previous picture was 120 centimeters dia, and this is 80 centimeters dia, out of which the core. Now this is a monolith, so it's a solid in which from top to bottom they're putting fuel rods and heat pipes. So heat pipes are the blue ones and fuel rods are the red ones. So as I told you that it's the heat pipes which carry the fuel, there's no pump over here. And this is surrounded by a reflector, again, something like beryllium. This is from the side. You can see the side view. So these are the rods. There's water on the sides and on top and bottom, and tungsten shield to uh, to protect the people in the environment from nuclear radiation. Now I'll come back to the design of this when we talk about shielding. But this design is by Evinci, and uh, they hope to just put it on a trailer and drive it off to some location where electricity is needed, and it's in the 1 to 5 megawatt electric range. So don't be surprised if in the next 5 years, and now it's 2020, so let's say by 2025, you could be seeing these kind of reactors. Okay, so by now you must have seen that nuclear engineering is really a fascinating field, and you can produce energy not only on Earth, but if 2-3 generations down the line, humans are living in Mars, so this is very promising for them. Okay, now back to the concepts of nuclear engineering. I have spoken about nuclear reactors, but I haven't told you about criticality, because first I just wanted to show you the applications of nuclear power. Now there's something called criticality, chain reaction, that if nuclear fission, if you can initiate nuclear fission, then in every fission, let's say you're producing 2 neutrons. So after 10 reactions, you'll have 2 to the 10, that's over 1,000 neutrons. And over 20, it's million. And over 30, it's 10 to the 9. So can you see that it's growing in such a tremendous way? So if you don't control it, you'll get a runaway situation. You'll get supercriticality, and that is a nuclear weapon. So that's not what you want. So what you want is that you don't want an uncontrolled release of energy. So what you want to do is that you want that to absorb the excess neutrons and to keep the system multiplication K, you want to keep this 1. In other words, if there were 2 people on this planet and you wanted to keep them just 2 people, so you would not let them multiply. But from 2, they became 4 to 8, and right now you've got about 7 billion people. So the multiplication of population is as it grows. So there are 3 regimes we talk about. We have K less than 1, and we call that a subcritical assembly, which is safe because the neutrons are going to die out, they're not going to build. Then, so that's K less than 1. Then you've got K equal to 1, which is criticality. When the multiplication of your system is K equal to 1, then the number density, the time-dependent number density is constant. And so you have a critical situation. And that is how you design a nuclear reactor. So the previous designs, and when I talked to you about PWRs and BWRs, so the first thing that you are required to do in nuclear engineering is to design a critical core. And same uh, for other things like a subcritical safe assembly or for a supercritical nuclear weapon. You start by, because you're going to first keep the weapon safe in a room, and so it has to be subcritical, but then you're going to make it supercritical. And if you see how it's made supercritical, then the implosion type, for example, if you look at the Fat Man design of Nagasaki, so what they did was that they had an external explosive which compresses the central uranium, and so you can compress uranium to increase its density. Yes, you can compress a solid as well. And so when you compress uranium, then it goes from critical to supercritical, and that's what a nuclear weapon is. If you do the engineering design correct, then you can make things happen at a time that you want them to happen. Otherwise, it fizzles out. So that's the challenge of balancing things in a nuclear reactor, in a nuclear weapon, and in a subcritical assembly. Now, it is important to understand that nuclear criticality, now this is very important because when I was a student, I used to think that nuclear criticality only takes place at, at a power level, at a power level. And now I know that criticality can take place at any power level that you make it, that you control it to. So you can have a 300 megawatt electric nuclear reactor, which is critical. You can have a 600 megawatt electric nuclear reactor, which is critical. You can have a 1200 megawatt electric. You can have a 1 megawatt electric nuclear reactor, which is critical. So criticality does not depend on the power that you get out of it. It's just a bigger and bigger system, and more heat is to be removed. Now let's look at example 1.11. So in the previous examples, if you have a million neutrons, then what calculations we could be required to carry out is to estimate the number of fission neutrons produced, the system multiplication, etc., etc. So you can look at this yourself, but I want to show you what is called a 4-factor and a 6-factor formula. Now look at this. The K, I just spoke to you about the K effective, about the K of a system. Now I'll talk to you about two K values. One is K effective, which is for a finite system, and one is K infinity, which is for an infinite system. Now for a finite system, you see we've got 4 factors here and 2 leakage factors. So this is a 6-factor formula. For an infinite system, which is so big that nothing escapes its boundaries, so we get the 4-factor formula. Now, this is a fascinating little picture that I want to show you, that what happens in the life of a neutron. So let's start over here when the neutron begins its life as a source neutron. Well, as I told you in lecture 1 that source neutron could be produced from MB or from CF252. Now MB or CF252 would produce neutrons with the spectrum which I showed you in lecture 1. So let's see, when they're very fast, then some of them leak out. So if the probability of a fast neutron leaking out is PF, for example, let's say it's 30%, and you have a million neutrons which are being produced. So 1/3 of a million is 30,000. So 30,000 neutrons would leak out, and the rest would stay in your system. So they would, some of them would let fast fission take place, and so there's a fast fission factor epsilon. So the 1 minus PF times S have now increased because some have been produced, some fission neutrons have come out. Now remember I showed you those horrible peaks, and I said they come from the excited states of a nucleus. So those were the resonance captures. So those horrible peaks are going to capture some of these neutrons. So some would go over there, and those that survive are what we'll call, multiplied this number by the resonance escape probability, small p. So now we've got epsilon times small p times 1 minus big PF times S. We've got so many neutrons. Now these have slowed down. Why? Because they were fast, they escaped resonance, and now they've become slow or thermal neutrons. Now when they've become thermal neutrons, some of them would leak out, just like those fast were leaking out. And this is a diagram made by myself, so it's not really very artistic, but I think it's fascinating because it explains to you the cycle that goes on. So the thermal leakage, there's a factor PT. So how many survive? It's all that, all this multiplied by 1 minus PT. Now, if these undergo fission, so first of all, there's so much material lying there. Everything is not uranium. There's some water, there's some steel structure. So the first thing you want to know is how many got captured in the fissile material. Let's say that's small f, the thermal utilization we call it. Now, so if you multiply this by small f, and then you have thermal fission, then eta times all that is what is produced. Now, eta is nu sigma F over sigma A. So the number of fission neutrons produced per neutron absorbed. So see, we started with S and we produced so many. So that's the game. So this is what we call the K effective of the system. So as you advance in nuclear engineering, one of your main objectives would be to ensure that K effective is 1. Otherwise, you don't have a nuclear reactor. So you have, at every design that you do, you have to compute, like I told you, the neutron flux. You have to make a system, you have to select your enrichment, you have to select your configuration, you have to place your materials in such a way that K effective should be 1. Okay, so that's the idea that of a design problem. Now, so you can look, you can read this yourself. And so in the early days, the historical days of nuclear technology, nuclear engineering, which was 1930s, from the time it was discovered in Berlin, and then Otto Hahn, Otto Frisch, Lisa Meitner, Strassman, then they moved to England. And I told you when I was a student, I shook hands with Otto Frisch in London when I was at Queen Mary College, and he died in 1979. I shook hands with him in 1978, I think, introduced by my professor, Dr. Jeffrey Lewins, who was at that time the president of the Institution of Nuclear Engineers in England. So, so these people came to England. From there, they went to America because you remember Einstein wrote that paper to US President Roosevelt that Hitler might design this thing. And so they went to Los Alamos and made the Manhattan Project. Now in the Manhattan Project, they started with small experiments. The first experiments that you can look at are where they determine the critical mass for bare spheres. And one of the first experiments was Godiva, and Jezebel, and Topsy. And for Godiva, for example, it's a, if you see over here, so Godiva, okay, Godiva is not over here. So I've got it somewhere over here. So anyway, these are for plutonium, and Godiva has a sphere of about 50. It has a mass of about 50 kg, and at about 93% U235, it has a radius of about 8.07 centimeters, if I'm not wrong. That's my memory. I could be wrong, but please do check that Godiva weighs about, okay, I think it's this one, 48 kg. But so this is the critical spherical systems which are reflected by 10 centimeters of uranium. So if you reflect it, then see you can reduce the core mass from 50 kg down to much less. So a plutonium critical mass could be made at 4.5 kilograms if you surround it by 10 centimeters of uranium. Of course, it would weigh very heavy. So critical assemblies can be designed. And if you look at a nuclear reactor, such as a pressurized water reactor, which I told you uses 2, 3, slightly more than 3% of enriched fuel at different locations. While the earlier ones, if you look at the early designs, they did not go beyond 1.1% fuel. Then typically they were quite large, and you could see some of these early Westinghouse designs. Okay, now futuristic space reactors, as I told you, could weigh very little, just about 300 kg. So this, I think, was what I wanted to say about nuclear reactors and nuclear criticality. So let me just summarize all this. I've spent the last 40 minutes or so with you, having gone through nuclear reactors for power production, for research, for propulsion, for space systems. And I've also told you that research reactors produce radioisotopes for medicine, agriculture, And then for diagnostics, they also produce radiation sources. So it's a fascinating and very, very vast field. From a nuclear engineering point of view, I'd say that in the design of nuclear systems, to estimate criticality and other reactions of interest, a full calculation needs to be done. And that is what this course is about, that you need to understand neutron diffusion and neutron transport. And then you'll see that when we design realistic systems, and sometimes you have to go beyond this. And that's why I put Monte Carlo simulation in here. So I'll stop this lecture now, and we'll meet again for the fourth lecture. Thank you.